So in the previous lesson in which we discussed the force on a current carrying wire, which had the formula F equals to ILB, that had the idea of the whole current moving through a conductor and eventually leading to a force. In this chapter, we're going to basically see what happens to the force on a moving charge, and we will see that how these two formulas are connected. These are exactly the same things. The only thing here is that we are considering the whole conductor in this case. And in this case, we're just looking at one electron or one positive charge. So he says, determine the direction of the force moving in a charged field. This can only be done by Fleming's left-hand rule. And by this time, we've already understood it, how it works. So these are the expected directions, for example. The cross represents that the direction of magnetic field is into the page. So if you were standing at this point, for example, then the magnetic field is actually going like this. So the north pole would be at the back side and the south pole would be in this side, so that eventually this field goes from north to south. So there's one way of looking at it. Okay, so if this is a positive charge and this is a negative charge, this is the direction of velocity that they already have. Notice that the charge needs to have a velocity. It needs to be moving in order to experience a magnetic force. If, for example, the charge was not moving and a magnetic field was introduced on it, nothing will happen. So the charge needs to have a velocity, because what we've discovered up to this point is that when the current is moving or when the charges are moving, they have their own magnetic field, which we found out by using the right-hand grip rule, of course, by the compass method, that if a current is flowing into the conductor like this, then there is a circular magnetic field around the conductor, which direction can be found by right-hand grip rule. Okay, so take a moment at this point and apply the Fleming's left-hand rule in this case to see where the positive charge is going to go. So in this case, the positive charge is moving upwards. How is it experiencing the force? So first finger pointing into the screen, the second finger will be pointing in this direction. And then when you open up your thumb, use your left hand. When you open up your thumb, you'll realize that this is the direction of the force. So the force is actually upwards in this case. But when it reaches at this point, for example, at this point, then the direction of force will be in this direction. So ultimately, and you can apply the Fleming's left-hand rule again over here by making sure that the direction of magnetic field is inwards. The second finger opens up to the direction of velocity, which is the direction of current, basically. And your thumb will point towards the left side. So what's happening in this case is that the magnetic force is changing its direction at all times because of the direction of the velocity. Because the charge is moving, it has its own magnetic field. So eventually we come to this point that charge in a magnetic field actually follows a circular path. Exactly circular path. So the things that I've written down over here as 1 and 5 means that this covers the first point and this covers the fifth point of the charge of the syllabus. Okay, so moving on to F equals to qvB. What does this mean and how it actually is formed about? You see, I told you that we come from the formula F equals to ILB. These are exactly the same formulas, but with a slight difference. You see, in AS, we have done that the current is equal to charge divided by time, right? Let's replace that over here in this formula and let's see what happens. So F is equal to charge divided by time multiplied by velocity multiplied by B, ignoring sine theta for now because we're assuming maximum velocity, maximum force, which can only occur at perpendicular angle, which is 90 degrees. So if I isolate this Q multiplied by V divided by T, sorry, not V, it is actually L over here. We have length over here because we are following this formula, right? So we have length over here, so length multiplied by B. Now notice that length divided by time is actually velocity. Distance divided by time is velocity. So this formula becomes Q velocity multiplied by B, which eventually gets denoted as qvB sine theta. So notice that the formulas are exactly the same. The only thing is that this represents for the whole conductor, for the whole piece of wire. And this only discusses the force on just one single charge out of that wire, which is moving. And this charge could exist in anywhere else as well. And what is this angle between? So the angle is between the direction of velocity and magnetic field. So if let's say if this is the direction of velocity, then the magnetic field should act perpendicular to it. Let's say like this, that there should be an angle of 90 degrees between velocity and the magnetic field flux. So we've covered point number 2 as well, what this formula actually represents. Now we're going to move towards Hall voltage and how we actually measure. Okay, let's try to solve a question using F equals to ILB first. before moving on to the Hall voltage and Hall concept. So in this situation, he says that a certain electron with a certain velocity is experiencing a certain charge, for example, and is present in the presence of a magnetic field that is 94 millitesla. The diameter of the motion is given, but the radius will be, of course, some division of this, which will be 7.5 centimeters. He says that show that the mass of one particle is 20 U. You see, 20 U, just a moment. Okay, so 20 U, we will get to that later what that is, but let's try to find out the mass first. So what's happening in this case, that electron already has its own force, it already has its own speed, but as it experiences a magnetic field in this gray region, it is going to experience a magnetic force towards the center of the circle, which will call for the centripetal force. So in this situation, just like in gravitation, what we've done, we have to identify where the force is coming from. So first mark will be gained when you write down that centripetal force. You have to mention this, that the centripetal force is equal to the magnetic force responsible for causing the rotation. So we will use mv square over r equals to qvB. Notice that I write down velocity like this so that it is different from voltage, because it's going to get confusing in the next topic. That's why I write down this small dash with the v so that it remains velocity and you know what it is. So over here we can see that this velocity is going to get cancelled with this velocity vector or this variable. What we are left with is mv divided by qr equals to b. Now since we want to find out the mass, I'm going to take every variable over there and replace every variable's value in this equation. So this is going to become m equals to qb divided by qbr divided by velocity. Okay, so so this is what it's going to look like. This r is going to go up, so qbr and divided by velocity. Let's replace the values and see what happens. So q is 1.6 power minus 19, b is 94 millitesla, so power minus 3, radius is 7.5 into 10 raised to power minus 2, divided by velocity was given to you as 3.4 into 10 raised to power 4. Now when you find the mass using this formula, you'll get 3.32 into 10 raised to power minus 26 kg. Now he says that we want to represent this in the form of atomic mass unit, and from nuclear physics we know that 1 atomic mass unit is equal to 1.66 into 10 raised to power minus 27 kg. What does this atomic mass unit mean? It means that either it's a proton or either it's a neutron. Inside the nucleus, they weigh exactly this much. Okay, so he wants to find out whether it is actually 20 times this mass, or actually how much times it is in comparison to the atomic mass unit. This value is given in the booklet. So simply divide 3.32 into 10 raised to power minus 26 with 1.66 into 10 raised to power minus 27. Your answer will be 19.9 times u, which is 20 u. So we've proven what we were looking for. So I hope we understand how to use the qvB formula in one of the applications. The next question, he says that sketch a uniform when the mass is 22 u. So let's replace this formula. Let's rearrange this formula again. So we had mv square over r equals to qvB. Velocity gets cancelled out. And the relationship that we are left with is, let's take r over there. So what are we left with? So m is equal to qbr divided by velocity, right? So since mass and the radius are expected to be changed, or this is what we are expecting in the equation, so the charge in the magnetic field is still the same, the velocity is still the same. So we realize that we come to the equation that mass is proportional to radius, which means that if the mass is increasing, the radius will increase. So this particle's path will be somewhat similar, but it will be a bit longer. It will be at a higher distance or a higher diameter in comparison to the first one. Okay, because it's heavier, it requires higher centripetal force. If the centripetal force is same, it won't be able to make a tighter or a smaller circle. Its circle will be larger. Now we move towards the Hall probe and its working and formula. This is point number 3 and 4 of the syllabus. This is a very thin slice of metal of semiconductor, but I've exaggerated the view so that we understand how this this proof is going to be about. So let's label this this side of the slice as T. Let's label this side as, let's say, L. Now, what's happening in this situation is that the current is being introduced from this side. And very most definitely what we've done is we've connected this cycle, we've connected this crystal with the battery. Let's say with the positive and a negative terminal like this at the base of the crystal or base of the slice. So we are expecting that the direction of current is actually like this. We are expecting that the current is moving in this way. But since we know that we're dealing with conventional current, so we are going to look at, or we're going to visualize the positive charges. Okay, so let's say that the positive charges are incoming into the circuit, that they are moving like this into this semiconductor circuit, and let's see what's going to happen. So if the current is actually moving in the circuit and there is no magnetic field in this situation, okay, there is nothing happening right now. Now, what if we apply a strong magnetic field from the front face in this slice like this? So the the positive charge wants to go down, but experiences a magnetic field that is in this direction at an angle of 90 degrees. So what's going to happen? A force of qvB, which is the magnetic force, will be experienced by this positive charge, and it will experience a force in a certain direction. Now let's see what that direction is. If you apply the Fleming's left hand rule, we realize that the magnetic field is into the page for this moving positive charge, right? And then you point the first finger into the screen, you open up the second finger downwards facing the floor, and then when you open up your thumb, you feel that the thumb is opening on the right side, which means that this positive charge, the conventional current, is actually going to experience a force in the rightwards direction, right? So this is a whole process. Just listen carefully and be focused over here. This is a whole process which eventually set up the all voltage, and we will see what's the benefit of that. So what is going to happen with these positive charges? So all the current or all the positive charges coming into the slice from this piece of wire or the piece of battery that we've connected are actually going to be pushed together, or they're going to be forced together to move towards this face of the slice or of this conductor, because all of them are experiencing a magnetic field, right? So what happens after this is that all the positive charges start gathering around on this plate, on this surface. And if, for example, we visualize the electron flow, we realize the current is going to come from this side. So the velocity will be upwards of the negative charge, right? So what's going to happen to the negative charge? Even if we had to visualize it this way, this is going to experience a force in the left direction. Or one way of, you can do this by applying Fleming's left hand rule again, or what you can do is you can see that if one plate is becoming more positive, then most definitely the next plate or the other side would become more negative in comparison to that plate. So again, there is going to be a time. Now observe that there is actually an electric field established between the sides. So the positive, when a charge actually comes at this station, right, it experiences a magnetic force which is because of qvB on the right hand side, which we found by Fleming's left hand rule. But since all of them or most of them accumulated on this side, now this side becomes positive and the other becomes negative. There is an electric field established between the plates, which is from left to right, because we know electric field is from positive to negative. Now what's going to happen in this situation is that more positive charges, if they try to accumulate on this plate, it's going to get difficult for them, because there are already so many positive charges over there. They're going to start repelling, or they're going to start you can say restricting the process of producing or accepting at least more positive charges in that same area. They will not be able to squeeze in more positive charges. So what's going to happen in this situation, that positive charge will start repelling and the negative charge will start attracting this positive charge. Eventually we can see and observe that this will be an electric force on the charge on the left side. So this will happen when there is an equilibrium position, when there is no more space. Under these magnetic field circumstances, no more positive charges can be forced to exist on this plate, and no more negative charges can be forced to exist on this plate. So at this situation, this charge will start passing straight through into the wire and then back to the conductor, back to the battery. So when this situation occurs, when everything is in equilibrium, we experience Hall voltage. And where is this Hall voltage? You see, from this surface, and from this surface. If we observe, we can connect a voltmeter at this point, and there is going to be a voltage, there is going to be a potential between these two surfaces. Right? So let's analyze this charge, what has happened with it. So on this charge, what happened was that the magnetic force became equal to the electric force. We know that the magnetic force is qvB equals to, and the electric force is QE. This comes from the chapter of electric field, which is electric field strength defined by force per unit charge. You take Q over there. So this is what the equation is going to become for the force. So we have also done one formula from AS. It used to be in AS, but now it's in A2. That voltage divided by distance is actually the strength of electric field as well. The distance between the plates, for example, positive and negative distance between the plates, and whatever battery they're connected with, their voltage. If you divide these two things, it will also give you the strength of the electric field between them. So what we're going to do, we will replace E with V by D, and I'm going to write down VH over here as a Hall voltage so that it remains separate from this V that we've written down. So this becomes Q equals to qvB. Q gets cancelled out from both sides. And what are we left with now? We are left with the velocity into B equals, and this D goes over there as well. So dVB equals to Hall voltage, right? So now we replace this velocity vector with respect to, from the AS formula, that I is equal to NAQV. So if we make V the subject of the formula, this becomes I divided by NAQ. This is a part of your course. That's why we're deriving this formula. That's why we can't use it directly. So V velocity, terminal velocity or drift velocity, is equal to current divided by NAQ. Now let's replace this velocity over here in this formula. What do we get after this? We get a formula that looks like this. So D multiplied by, now V is I multiplied by B. You can see that I is going to be in the numerator and the rest of things are going to be in the denominator. So NAQ equals to Hall voltage. Now we've established that this distance D is actually the distance between the plates, which is going to be the distance L. And to find the cross-sectional area of this face plate, because this is where the current is actually moving through, the cross-sectional area will be L multiplied by T. So I'm going to replace this distance D first with the distance, with the variable L, because that is the distance between the plates. Okay. So L dot I dot B divided by N, and the cross-sectional area is now L multiplied by T multiplied by Q equals to VH. Now we see that L is going to get cancelled out and we are left with the formula VH equals to IB divided by NTQ. This is the thickness of the slice that we're considering. So that is how we derive the formula for Hall voltage. Again, the purpose of this idea, why are we actually doing this? You see, if I make B the subject of the formula, what do we get? We get B equals to NTQ VH divided by the current I. What we are trying to do, we are trying to find out the magnetic flux density. We don't have an equipment to measure this. You see, we know the charge density of the semiconductor we will use. We know that the thickness of the slice that we have used to mechanically construct this. We know the charge of the electron that is moving through it. We know the current because we've connected an ammeter. We know the voltage because we've connected a voltmeter. So when all of this is measurable by physical quantities, we will measure them and then find magnetic flux density directly or indirectly in this way. Okay, so what's the end goal of over here? That magnetic flux density is proportional to the Hall voltage. If the magnetic field is stronger, if the Hall probe is placed somewhere where the magnetic field is stronger, the Hall voltage will be higher, which can be calibrated on a simple scale of a voltmeter. That if the voltage is higher, most definitely we can use the formula and give them the values of V. That if the voltage is 0, the magnetic flux is 0, the voltage is 1, probably that is 0.1 Tesla. And this is, let's say, 0.2 Tesla, 0.3 Tesla. So a voltmeter will be calibrated to show the magnetic flux density. Okay, so now we move on to the question of the magnetic flux density. This question is easy. Don't worry about this. This is going to be a repeated question again and again. He's going to ask you where the electrons are going to go. So notice that these are the electrons Okay, and the magnetic field is coming from the upper side. So let's apply the Fleming's left hand rule. You'll have to use the left hand. The magnetic field is downwards. The first finger will be pointing to the floor if you're sitting down. The second finger will be pointing towards your right side. You should point the finger towards the right side. Why? Because the electrons are in the opposite direction to the positive charges. We assume this rule, the Fleming's left hand, with positive charges. So I'll have to invert the direction of current, or you want to do it the other way and then invert the answer at the end, your choice. So when I open up the thumb, I realize the thumb is actually pointing into the page somewhere here. So what's going to happen to these electrons? They're going to come and they're going to settle down on that face. So I can see that the negative charges are actually going to accumulate over there. The positive charge will be accumulating over here. He says use the letters to identify which surfaces will be used for the Hall voltage. So as we can see that one surface has positive, one surface is negative. These surfaces, if I connect a voltmeter, will be used to represent the Hall voltage. So I just have to use the variables names, which is PSVY. So PSVY will be the one phase and QRXW is the second phase. It says state explain whether the phases name in A1 is which one is more positive. We use the Fleming's left hand rule. We realize that PSVY is more positive. So PSVY is more positive. Why? Because we use Fleming's left hand rule, and electrons gather at the opposite phase. Name that phase. WQRX. And if you can show that on the diagram as well, that would be nice. He says identify the letters being used to represent. Okay, so one thing that I probably haven't discussed up to this point, what is this N? Although this is already discussed in AS, electricity, this N is charge density. Charge density. What it means? It means number of electrons or positive charges, if you're considering conventional current, divided by volume, which is in a meter cube. So how many electrons does it have? How many charges does it have to offer for setting up the Hall voltage? Okay. So then he asks you about the identify thickness T. So in this case, the thickness T will be this way. Whatever surface the Hall voltage is set up, its diagonal, its alternate length is the thickness, as we have done in this case as well, that this was labeled as the thickness of the slice. So over here, the T will actually be PV, SY, RX, QW, whatever variable you're comfortable with, you can use that over here. It says state the meaning of N. Again, charge density is the number of charges per unit volume. You can write this down over here. State and explain effect if the polarity of the Hall voltage when negative charges are introduced and replaced with positive charges. Would it matter? No, because in this case, we were considering negative charges and Fleming's left hand rule told us they're going to go towards that side. If we use this Fleming left hand rule again with positive charges, let's see what happens. So the magnetic field is downwards. The direction of current is this in this direction. So if you do that with your left hand, right? So the direction of current, and second, the thumb actually points like this. This is the direction of thumb. So this positive charge is going to come to this face. So it does not matter if you change the negative with the positive, the Hall voltage or the setup of the Hall voltage remains the same. It does not matter. Okay. And you can check out this question. This is from February, March 2018. This is a repeated question. That's why I've included in the lesson. The last topic of our course of this chapter is we have done point number 4. We've done point number 3. We are looking at now velocity selection or velocity selector. You will notice that in this question that we did in the very first part, it says that there is a mass, there is a specific charge coming from a velocity selector. Now, how do we decide what type of what velocity of the electron is going to be? So how do we do that? We do that with the help of a velocity selector. So what we do is that from thermionic emission, of course, we have thermionic emission equipment that we did in O-levels CRO as well. Electrons are being released into this box, into this container. Okay, so we know where the electrons are coming from. Now the problem is that these electrons are coming at various speeds. They could be moving faster, they could be moving slower. We don't know their velocities as yet right now, but there is a pinhole, for example, at this location. I want an electron of a very specific velocity so that I can carry out the experiment. But how do we do that? How do we filter the electrons that are coming infinitely from the other side of the thermionic emission process, from the hot temperature filament? How to do that? So what we do is we allow these electrons to come. For example, they're moving inside the conductor like this. So I'm going to isolate from one charge only. So let's say that there is one negative charge over here. Okay, let's say that the direction of velocity of the charge, the direction of velocity of the charge is exactly in front. This is velocity v. Let's apply a magnetic field from this direction. This is exactly what we do in Hall voltage as well, but right now we're going to use this for velocity selection. So how to do that? So if the magnetic field is actually perpendicular to the direction of velocity by making an angle of 90 degrees, we'll have to apply the Fleming's left-hand rule to find out the direction. So the magnetic field is into the page, direction of the second finger is towards the right side. So magnetic field, direction of current, although this is a negative charge, we will assume opposite direction eventually. My thumb opens in the upward direction, but we will assume the opposite direction. So the electron is going to move towards the downward side. So the magnetic force is downwards. Now, when we do this, over in the Hall voltage setup, we waited so that these electrons will gather on this surface and positive charges will gather on the top surface, and then the voltage will be set up. Over here, we're going to do the opposite. We're deliberately going to apply an electric field on the other side so that this electron moves straight ahead. What should I do so that I can counter this magnetic force? I should apply an electric force in the upward direction. And how can I do that? By applying a positive voltage to the top surface and applying a negative voltage to the base surface so that the electron can be repelled from downward side and be attracted from the upward side. So what happens now? Let's say that the magnetic force and the electric force of this electron are exactly equal. So this electron will pass straight through the spin hole. For example, if the electric force of a charge is higher, then this electron will move in the upward direction and get absorbed in this surface. If the magnetic force is higher, then this charge will actually move towards this downward place and get absorbed. This side is actually grounded. So any extra electrons that are being received on the surface are actually going to be grounded. It doesn't matter. It doesn't affect the process. So only those electrons that are going to have exactly the same electric force and magnetic force will be able to pass through. And I will decide the velocity at which this happens. You see, the magnetic force is qvB. Now the charge is same, the magnetic field is same. I'm not changing them. So if I increase the velocity, the magnetic force increases. Okay. So any electron that has the velocity greater than the certain value that I am looking for, its magnetic force will be dominant and it will move downwards. Right. And if, for example, I'm looking for an electron in which the velocity is less, then the magnetic fields will be weaker and the electric force will dominate and this is going to go upwards. So only the electron with a perfect combination of electric and magnetic force will be able to pass through. So for that, I'm going to think that magnetic force becomes equal to the electric force. The magnetic force is qvB. Electric force is qe. So since I'm looking for velocity, q cancels out. We are looking for velocity. Velocity is equal to e divided by v. So velocity will be of my choice, and I can choose any one of them, either electric field strength or either the magnetic field strength. The ratio of E and B actually gives me the answer of the velocity that I'm looking for. So I will choose one variable and control the electric field by connecting this, for example, by connecting this to a battery over here. So I can tune any two of the variables, either electric field or either the magnetic field, to eventually control the velocity of the electron that is going to come out. That is how you select the velocity of the electron that you want instead of all the electrons coming towards you, rather like a filtering process. So you will see the same question in May, June 2018. Actually, this is a repeated question. So he will ask you about the velocity selector in this way. You can look at the marking scheme and then you will see how to answer this question, but I've explained the theory to you, how it is actually working.